You failed already. I'm sorry.
Cameraman for 2 seconds. Okay. Yeah. So before we get any general questions?
4B from Spring 2005.
Oh, you guys are working on Spring 2005 for what?
B.
Yeah. I mean, you won't need to do that. You don't need to know that.
Okay. What's that?
There are 4B from Spring 2005. Like I said, this exam, it really emphasizes 392. There's not a lot of stuff that directly comes from Calc 3, so
Yeah.
the few things that do come from Calc 3 we're going to cover today.
Okay.
But the most general important things are, you know, Stokes theorem, Green's theorem, divergence theorem. That's guaranteed to be on it. That's in part 2. And you have to know how to do line integrals. You have to know how to do everything with matrices, inverses, determinants, and using determinants. And solving systems, of course, is on it. It's pretty much what you would expect in general, but a lower emphasis on Calc 3. So the finals where they do a lot of Calc 3 stuff, those parts you can ignore for the most part, but pretty much everything else, as expected.
Would you do an example of the mass, center of mass?
Oh, yeah, sure. I was going to do one of those. Let's make this one up off the top of my head. So let's start with Calc 3 then. Mass and centroids. Alright, so center of mass, it's called centroid if in 3D or pi. Right? So if you see the word centroid, it's the same thing as center of mass. But yeah, like we said, there were basic formulas for it, and I actually came up with an example. I gave you the formulas last class, so I'm not going to repeat them. But an example was, I just came up with one. Let S be a solid region bounded by cone and sphere. So just some couple nice surfaces, don't have to go really crazy. Like I said, your exam didn't really go, there was nothing really crazy. So if you know how to do it for your standard surfaces, you can pretty much figure out how to do it for everything else. This is the region bounded by this cone and that sphere. Suppose the density over S is given by dx y z equals z or something like that. Right? So another way they could actually say this is the density at any point is given by the distance from the xy point. Right? It would mean the same thing. Right? And then a question could be to A, find the mass of S, and B, find the centroid. So you might have an equation with a problem looking like that. So how do we do it?
Well, wouldn't the mass be given by volume? Volume times density. So we do each integral with the density function inside of it.
That's correct. Do we know what our thing looks like, our system? Our solid. Because a lot of times drawing the picture helps you to set up the integral. So what would it actually look like?
Cones and a sphere of cones and.
Right, so we know what a sphere looks like. Radius 1, that's fine. Okay, so it's just a circle. Right, that's our sphere. What does that cone look like?
It's inside.
What does it look like? Where is it opening along, et cetera, et
It's
cetera?
opening along the z-axis.
Down?
Up.
Yes, it's going up. Okay. All right, so the actual region that we care about is this part here that sort of looks like an ice cream cone, right? Right? That's actually the part that we're talking about, right? So it's bounded by, I could say below, by the cone and above, to be more specific, right? So the bottom part of our solid is the cone, top part is the sphere, and I actually want to compute the mass and center of mass of this guy. Of course, there's going to be an intersection at some point. And that's going to be our region of projection. That's going to be, give us what it does with this. How do you find that intersection?
We don't really need it. Can we just have a bound being the sphere and a lower bound being the cone? A surface over another surface?
You're going to have a triple integral, right? So
yeah.
Let's do this. So part A is the mass equals m. And I know m would be the triple integral of the density function. How do you set this up, first of all?
Well, the first integral will just be the domain, and the third integral will just be the top.
Sure. This guy would set up D. This guy would go between surfaces, right?
Yeah.
The bottom surface, the top surface.
Yeah, definitely.
Okay. Now, this is how you set up in rectangular. What do you do rectangular coordinates here? What coordinate system do you think you would use?
Polar. Well, it's really, yeah, polar, actually polar. You want to do spherical, but I like polar better.
Okay, let's do polar. What would we see in polar? Right, so rectangular wouldn't be the one we use. Right, it would be either polar or spherical. Let's think of doing it in polar. How would it look?
0 to pi, and then the first will be theta, 0 to pi, and then the second will be r.
How do you figure out r?
Well, you could say z is equal to x squared plus y squared. X plus y squared is r squared, so z is equal to r. That's for the surfaces. I'm thinking 1. It's only 1. R is going to equal to 1.
D is given by this circle, right? In the xy plane.
Yeah.
Right? Where did that circle come from?
0 to r.
The intersection of the two dots.
And
If you want to find the bounds that do with r, you have to find where they intersect.
Ah, true.
Right? So how do you find where they intersect?
Equal them. The
Right.
equations.
So let's look at the intersection. This means that from the first one, you know that z squared is equal to x squared plus y squared, right? So you can plug that into the sphere. So this is x squared plus y squared plus x squared plus y squared equals 1, right? Which would imply that x squared plus y squared equals a half. Okay? So then,
it's a half, okay.
so what is, so theta would be what to what? 0 to 2 pi, that's obvious. What would your r be between 0 and 1?
0 to 1/4? I'm sorry, 0 to 1 over radical 2.
Okay. And your z would go between what and what?
The lower surface is a cone, so it'll go between r and...
Right, so x squared plus y squared is r squared. Take the
squared
radical of
to
that, you just get r, that's the bottom. Right, and the top part?
Will be r squared
One.
plus z is equal to 1. We look for z, so it'll be radical 1 minus r squared.
Right, just solve for z. Here, we know it's just the top part, so we take the positive radical and we get the top. And so we could say the mass is equal to 0 to 2 pi, 0 to 1 over radical 2, r to the radical of 1 minus r squared of our z, right? This guy is just z, so we just get z r. And you do that.
Well, dg, dr, dg.
Yes.
If you had a circle, it would have been a lot more work.
Hmm?
If you had a circle, it would have been a lot more work because then we have to actually plug in what z is.
What if you wanted to do spherical?
Okay.
How would you do it with spherical? What is the equation of the cone in spherical? Right, so first remember with spherical, how is it set up?
Roll.
theta, rho, and phi.
Right, so you have rho, theta, and phi, right? What is rho?
Rho is the
Distance from the
yeah.
origin to the outer surface, right?
So that'll be
It's
1.
always going to be constant because you're measuring the outer surface is always a sphere,
So it'll be 1.
right? So your rho is just going from
0 to 1.
0 to the radius of the sphere, 0 to 1, right? What about your theta? Theta is the same guy like in polar coordinates, right? The theta interpretation doesn't change. So your region of projection is a circle, it's a full circle, so your theta is just 0 to 2 pi, right? What about phi? How's phi measured?
Oh.
0 to pi.
It would be easier. It would have been 0 to pi over 2.
Yeah,
0 to pi over 2, wow.
No, 0
I mean 0 to pi over 4. 0 to pi over 4.
0 to pi over 4, right? We already know the standard cone is always pi over 4 for that guy, right? If you didn't, you could figure it out actually, but
Yeah, but I
you
don't know what it says here.
right? Because right here you know that z equals r, right? The radius of the cone, but z also gives you the height of the cone, right? So basically, if you take a slice here, you have z here and z here, right? And your phi would be the angle here, so you could just say tan phi would be z over z, which would be 1, which implies phi is equal to pi over 4, right? Because you know you're in the first two quadrants, right? So this would be 0 to pi over 4. So all your limits in spherical would be constants. And so in spherical, what your integral would look like is theta goes from 0 to 2 pi, phi goes from 0 to pi over 4, rho goes from 0 to 1, of z, which is rho cosine phi, rho squared sine phi, and rho d phi d theta, which you could simplify that down. Pi over 4, 0 to 1. 1/2 q sine. And either of those you compute the integral and you will get the mass.
1/2?
Yes.
Oh yeah, because 2. Yeah.
Right, since sine phi times cosine phi is equal to 1/2 sine 2 phi. Right? Because you know sine 2 phi is equal to 2 sine cosine, right? Sine 2 theta is equal to 2 sine theta cosine theta. So if I just have the sine times the cosine, I can change that to this guy, and it will be a lot easier to do. Right? And of course you can evaluate the integrals. If you wanted to find the centroid, how would you do it?
Centroid?
Yeah.
Uh,
So centroid is exactly the same integral except, right, you're going to multiply by an x here,
or z.
right, for the x coordinate. You're going to multiply by a y here and integrate for the y coordinate. You're going to multiply by a z here and integrate for the z coordinate.
And divide by mass.
And then you take 1 over the answer here. But the thing is here, you actually don't have to do x and y,
It's
right?
symmetrical.
Because it's symmetrical, right? So I already know here that x bar equals y bar equals 0, right? Because if you're looking on the xy plane, right? My density function is given by z, that's symmetrical on the xy plane, right? It's always at a different level, you get a different thing. So the x and y bar are directly at the center. The only thing you have to find now is the z bar.
So does that mean that we get already 2/3 of the answer?
Yeah, so you know the center of mass is going to be 0, 0, something.
So that means we get 2/3 of credit immediately.
Yeah. Well, if you saw that, right? If you actually did this whole integral, it would take you forever to get 0, but you should just see that, hey, you can use symmetry here.
So that means if we get everything else wrong, we get that right, we at least get 2/3 of that 1 point.
So this would be z bar. No, I wouldn't give credit for this, because it's something that you're expected to see. Right? So this part here would be z bar, but that would just be 1 over m, which is going to be the previous answer. You can either get it from that integral if you want polar, or this integral if you want spherical, times the triple integral of z times d x z over s. In other words, since your density function is actually z, you're just taking the integral of z squared in this case. So here you would have rho squared cosine squared And then you can use a substitution. The integral actually won't be that bad if you keep the spherical. Right? So especially when your region is a part, comes from the part of a sphere, spherical is usually going to be nicer because you're going to have all constant limits. So, yes.
Which one out of these two, like polar and spherical, would you advise us to do? Like, would you recommend?
The same.
In this case, they're actually, either would be okay. Let's see. I mean, here, yeah, because here, if I integrate with respect to z, right, I would get a z squared, which is going to kill that radical anyway. So I'm not going to have radicals or anything. You're really integrating polynomials. And here, it's just integrating trig. In this case, it's not really much of a difference. There are other times where it might be messy in one than the other, though. Like in general, here, when you have limits where you have functions to plug in, it's usually in general more complicated than if everyone's a constant.
Especially, imagine if you did use rectangular.
Oh, you wouldn't even think of using rectangular here. Because you have the radical of 1 minus x squared minus y squared. You probably have to do trig substitution, all sorts of crazy things. Yeah, so I wouldn't even think of using it, right? So you think of using polar when your region of projection is a circle. You think of using spherical when your solid is bounded by a sphere.
It's like we barely use rectangular anymore.
Not in cases like these.
No, we like haven't really used rectangular much at all, actually.
Yeah, that's true.
In
theory, it could come up, but yeah, they usually talk about spheres and cylinders and
harder.
These guys sort of lend themselves to polar coordinates.
We didn't have like any sample final problems with, that deals with center of mass. So
no. So from here, if you want problems, you go back to Calc 3 finals. Right? But it's guaranteed to come up on a Calc 3 final. Every single Calc 3 final has a problem with this. So if you really want to get your practice on this, just look up the past finals for Calc 3. Anyone will do because they always put a question like that in a Calc 3 final. So yeah, that's basically how to do it. Now let's move on to 392. Right, so this is just a quick review of Calc 3. This is how you compute these guys. And so 392. You guys want to start with linear algebra or go back to vector calculus?
vector calculus.
Okay. So yeah, it's been forever, right?
No, it's only been a couple.
Yeah, I mean, we finished all of linear algebra in like
What is it?
4 classes, and we were really like taking our time with it. I mean, the last class I only did like one kind of problem. Yeah, vector calculus was really relaxed. Yeah, so important things in 392. Really, you're going to want to know a part of this, the final. It really tests your knowledge of concepts of what's going on, right? So you really have to know, of course. As always, parameterization. Of curves and surfaces. Right? This should have been stuff you've mastered since exam 1 and so on and so forth. But a lot of people were having trouble on this even up to exam 3. Right? So you know, if you have you're parameterizing a curve, how many parameters do you have?
1, 2. Well, really just 1, T.
1. Right? So example, you can parameterize a curve using R and T, where T is some parameter. How many parameters are you parameterizing a surface?
2.
Generally 2, yeah.
2. Right? The general form we call this was R of U and V. Right? There were some times when on the 3rd exam, I think, where you had to you were parameterizing a curve, some people, not everyone, but there were some people who were parameterizing curves and they had 2 variables in it. It should be obvious it's not a curve, it has 2 variables. You're parameterizing a curve, there's only 1 variable, right? And we dealt with basically 3 different kinds of parameterizations that will come up, right? So we know how to parameterize things with circles, use sine and cosine, things with straight line, use that formula, and with pretty much everything else, you try to solve in terms of an independent variable. And
you can't just make x, y, and make your z function a function of x and y.
yeah. And there are a lot of formulas that comes from that particular parameterization, which we're going to talk about. You should also know the kinds of integrals. In particular, f dot dr always shows up, right? Green's theorem and Stokes' theorem talks about this guy, right? And so, what are the steps to compute this integral? How do you find
Look
it?
at the problem. The problem tells you exactly what to do. Find the
Exactly.
function,
Right.
find
So
the r.
first, you find r, right? And of course, in order to find r, you have to know how to parameterize, right? So they're not going to. A lot of times, they're not going to give r to you. They're just going to describe a curve, and you have to know how to set up the r, right? So if they describe a circle, you should know how to parameterize a circle. If they describe a straight line, you should know how to parameterize a straight line, etc. Right? So the first thing you do is you find the r, then you find the dr, which is just the derivative. Then you find f of r t, right? Then you dot product. And then you integrate. Right? These are always the steps, right? So if you see an f dot dr thing, it shouldn't be something you have to think about. You know exactly what you have to do. Find the r, find dr, find f of r t, dot product, integrate. All problems are like that for this guy, if you want to do it directly. Right? This is talking about the doing f dot dr directly, right? So for example, in part 2, they'll say, you do f dot dr directly, they mean do this, right? Parametrize and do the dot product and integrate. Of course, there are other ways to do f dot dr. Green's theorem was one of them,
Or two, actually.
right? This was to compute f dot dr in 2D, right? What were the conditions? How do you know when you can use Green's theorem?
It has to be conservative. No,
No,
sorry,
you don't
it
need
has to-
conservative.
Yeah, it has to be positive orientation.
It has to be
Clockwise.
Just not closed. The curve has to be closed. Of course, we're assuming piecewise smooth. Right? So if you're in the plane and I describe C as just this curve, do f dot dr along that. You cannot use Green's theorem. Right? Green's theorem does not work.
Why can't I say
Right?
conservative?
But has nothing to do with conservative. Green's theorem you don't care about
but
conservative.
conservative then is closed. It's conservative then is closed, isn't it?
What do you mean?
If the function is conservative, it's going in a loop, so it has to be closed, doesn't it?
No. No. The function and the curve are two very different things.
Oh,
Right? Remember, the function is a vector field, right? It just gives you a field of arrows all over the place, right? It's different from the curve itself,
okay.
right? We know that if the function is conservative, then the integral around a closed curve will give you 0. But the function and the curve are different, right? The curve is just the path you're taking along, right? But you know, if your C is just a nice closed curve, like this is C, then yeah, yes, for Green's theorem.
Does like simply connected and connected, those sort of things apply here?
We're always going to give you things that are simply connected.
Okay.
and connected. So you don't have to worry about that.
Do you think
In general, it does apply, but in 392, they'll always be the nice.
What if the curve goes in OR?
Negative negation?
Yes, so it's not like in the first octave, but first order, right? It goes like into negative y, or what is the, how we set up the integral?
Example? What do you mean? Like your curve
Exactly.
goes in more than one quadrant?
Exactly.
Like a boundary of this region? Still, you'd set it up the usual way. So in this case, if this is a circle, I would use polar coordinates, right? R goes from 0 to the radius, and theta would go from what to what?
3 pi over 2.
0 to 3 pi over 2, right? So there's still, even if your region covers several quadrants, there'll still be nice shapes that you know how to
So
parameterize.
it's going to be a circle, right? It's not going to be like a parabola or something crazy.
They could give you a parabola, but something like this, they could give you a parabola sliced by a line, for example, right? That still wouldn't be a problem. You'd set that up in rectangular coordinates, though. Yeah. But it doesn't matter. As long as your C closes a curve, then you can use Green's theorem, right? And there are problems on the exam that really is going to test this concept. I mean, they'll like ask you a problem, for example. There is no problem like this, but for example, they could say, oh, you know, do this line integral, do this f dot dr, right? But if you try to do it this way, it's going to be really complicated. But you're the one who's supposed to recognize, well, the curve is closed, which means I don't have to do it directly. I could do it Green's theorem, right? They're not going to specify which way you should do it. But just because you know that, well, you know, it's sort of hard doing it this way, they never said I couldn't use Green's theorem, right? So let me just use Green's theorem. And then you do it Green's theorem way, and it's really easy, right?
So we're not going to be like, use Green's theorem only or do it directly?
In part 2, they'll definitely ask that. Part 2 is always the same, right?
Okay.
Do it directly in Green's theorem. But in part 1, they're really testing your knowledge of concepts here. So sometimes they're going to ask questions where if you just do it the obvious follow your nose way, it's really hard. But if you know that you can actually switch it, then it'll be easier, right? But they're not going to tell you that you can switch it.
Okay.
But it comes down to knowing the concept. So that's why when you just say Green's theorem, don't just memorize the formula, memorize when you can use it. Right?
We can talk about conservative and non-conservative vector fields when we're talking about 3D. If it's 2D, can we do that?
Come again?
We can talk about using conservative vector fields for 3D, not for 2D.
You can do it for 2D.
Oh, so
right?
it still works.
So if you have a closed curve and you know your f is conservative, which you have to do the check, right? You have
Yeah.
to check that partial with respect to y is equal to partial of q with respect to x, right? So,
You call a potential function and then do the endpoints.
yeah, exactly. Right? But if it's a closed curve, the endpoints are the same.
So it'll be 0.
Yeah, so it would be 0 automatically.
So,
You don't have to do it.
in this case, it'll be 0.
If you have a closed curve, if your f is conservative, yes, it will be 0.
Okay.
Right? Because Green's theorem would say that f dot dr is equal to the double integral of qx minus py, right? dA.
And P and QX and PY are the same.
Right, but conservative means qx and py are actually the same thing. So right away you get 0.
Okay.
Right? So
we
if
don't
you
really
thought of doing this by Green's theorem, then you immediately get 0 here, and odds are your function will be conservative, but it doesn't matter.
No, so just, you would recommend just check it. You would recommend just do Green's theorem, not it.
No, I check it, right?
Either.
I first recommend that you follow instructions, right?
Oh.
If they say do it directly, you don't have a choice. You have to do it that way, right? But if they just say just do this line integral, then you can look at it. Well, what are the tricks I can use, right? And the tricks you can use comes from knowing when you can use each thing, right? So Green's theorem only works if the curve is closed. So that's one thing you should do. So in fact, if they ask you compute f dot dr along this line, right? They give you this curve here. Then you know you can't use Green's theorem. It's not in your bag of tricks anymore. You also can't use Stokes' theorem because Stokes' theorem is in 3 dimensions, and your C also has to be closed, right? And of course, divergence theorem is not going to help you. Divergence has nothing to do with f dot dr, right? So then you'd think some other theorem, you know, maybe the f is conservative, and I could just use the endpoints or something like that, right? So it's just you just need to know when you can apply each concept, right? I mean, if you do things directly, you'll get to it, but it might be more difficult. Knowing the concepts will really help you out.
You still have more time with this, right? Like this test is like they take out some stuff so it'll be quicker, or no?
It would feel like you have more time because you actually have less questions in this one, I think.
Okay, so
Like finals, you usually do 9 problems. I think this final has 8 problems.
Oh, great! So that means
8 required problems.
So that means
So you have a little more time to actually think about it, which is good because the questions are going to test your knowledge of concepts more. It's not just straight computation. Sometimes straight computation will get you into trouble on this exam. But like at the end of the day, like I said, they don't give you really mean functions or anything, right? If you know what to do, it'll be easy for you to do it.
No, so that means it's definitely possible for most of us to get 100 in the exam.
Oh, it's very possible to get it, yes. Right, so you should know that. And you should, so remember Green's theorem is doing this way because this guy is equivalent to, Green's theorem might look like this form, right? Q dx dy, right? Along C. But this is just if you use your R to parametrize as x of t, y of t. Right? If you let your R be parameterized in terms of the x coordinates and y coordinates of the curve, then it's equivalent to them.
You mentioned a while ago that that form of the line integral is actually the natural form.
Yeah, this is like the most general form of line integral in all dimensions, right?
I thought you meant like in terms of nature, like if we actually were to compute problems of that related nature, like using physics, then it would usually be that form.
Yeah, it will be this guy. Right?
Okay.
Your textbook tells you this guy to emphasize that it's 2 dimensions. You're only thinking of in terms of x and y.
Alright.
But it's really computing that guy. It's computing work. Right? The work around a closed curve, you can use Green's theorem. That's basically what Green's theorem says.
When we integrate like surface integrals and all that stuff, and we have the integral set up, and it's just a constant, we could just know the area formula for whatever the shape is and just plug
Yeah,
it in,
so
right?
you can know that the volume is equal to the triple integral of 1, and you can know that area is equal to the double integral of 1. Alright, so if you have a constant function, you can always factor out the constant. If your region is nice, like a circle or something like that, you know the area. You don't have to actually compute it. But even if you did, you could do it. It shouldn't take too long. But yeah, you can know those concepts. But Green's theorem says this, and you should know when you can apply it. It does not always apply. It applies when your C is a closed curve. Right? Piecewise smooth and all that, but they always give you piecewise smooth. And Green's orientation matters, right? You know, if you have negative orientation, it means you put a negative sign. That's the only difference, right? So it's set up for positive orientation, but if you have negative orientation, it doesn't kill everything. You just negate your answer, right? And remember...
In this case, it's negative.
Yes, in this case, it's negative orientation. Recall also positive orientation of closed curve equals counterclockwise. Right? If it's clockwise, then you can set it up as if it were counterclockwise and just negate the answer.
And the reason we even decide it being positive is the right-hand rule, right?
The right-hand rule helps you with Stokes' theorem, not
But it's still clockwise either way. Clockwise is still coming up, so it would still technically be positive.
we're in 2 dimensions for Green's theorem. It doesn't really.
No, it's that little thing I picked up.
Yeah. So anyway, what about positive orientation for closed surfaces?
Oh, putting out.
Alright, so there's a difference when you have a closed curve from a closed surface.
You
Right.
have a normal vector.
Yeah, not putting out.
Outward pointing normals, right?
And if it says it's positive orientation, then you know it's a surface. You know
Right.
it's closed.
And do not confuse outward with upward or downward. It can mean either, right? It depends on how your surface looks. So for example, if I tell you, oh, it's bounded by a paraboloid and a disk at the bottom, right? Then there are 2 situations. Here, outward would mean up. But here at the bottom, outward would mean down. Right? So you just have to know. Draw your figure and then figure out if I'm pointing outward, would I be pointing upward? Right? So that's another concept you should be aware of. So yeah, to compute Green's theorem, C must be closed. It must bound D. Right? That's the relationship between the curve and your region. Your D has to be bounded by the curve C. Right? If you have those conditions, you can use Green's theorem. Right? Otherwise, you have to do it directly. What do you know about Stokes' theorem?
One question.
Yes.
If C is a closed curve, doesn't it automatically imply that it is bounding D?
Come again?
If C is a closed curve, doesn't it automatically imply that it's bounding D?
In general, no. But on your question, on your final, yeah.
Okay.
Yeah. So the question will say C bounds, let D be the region bounded by this curve. And then you know, oh, Green's theorem would apply.
And of course, if it's pointing upward or pointing downward, it's going to conclude that's not really closed.
What is up or down?
Like if they told you that, for example, you have a surface that's only just pointing up or down, it's going to conclude.
Oh yeah, well that's in Stokes.
Yeah.
So what do we know about Stokes? First, what's the equation?
Stokes is the double integral of curl of f dot s, no, curl of f dot n dn.
That's not an equation.
That equals,
Yeah.
F that.
F dot
F dot dr, the work integral, is equal to the double integral of curl f dot ds.
which is
What is
n dot
S
d.
and what is C?
S.
So it's the
S
surface.
is S, yeah, S is the surface.
S is a smooth surface bounded by a closed curve C, right? So you have a surface and the boundary curve of that guy is C. So this is your S and the boundary of that is C, right? In that situation, this applies, right? In no other situation does it apply, okay? So you should know when you can use Stokes theorem. This is the equation, right? That you can compute work by doing that if this condition is fulfilled, right? So that's basically what Stokes theorem says. So someone might say, compute the work and this is the situation, right? You should know that you could do that. If you're doing it directly and it's complicated, you should know that you can switch to that, right?
And ds is also going to be nda.
Yeah, ds would, yeah, this is equal to, yeah, that's a good point. Let's talk about that first. Okay, so if you're looking at this guy, which is the same sort of integral, except instead of f, you have curl f. But this, remember, we said it was equal to f dot n dA, right? And your n you can compute in two different ways, right? Based on what situation you have, right? If S is parametrized,
You get partial cross partial.
Right, so have to parameterize means your normal vector isn't pointing up or down, you can't tell, right? Or it's pointing both up and down at different points in your region. Then it's more useful to parameterize. Or if it's given, right, by this parameterization, then your n would be equal to r sub u cross r sub v. Or the negative of that guy. You just have to, check. Okay. If S is given explicitly, example, as z equals f of x, y, right? Meaning, once you can solve for one of the variables, you can actually do it this way. And so your n would be minus fx minus fy positive 1. This is for up. And it would be fx fy negative 1 for down. Right? In the vast majority of cases, this will work. Right? In fact, we developed this formula by using this. Right? We said if you just parameterize by x comma y comma f of x y, this is what you end up with. So a lot of the work that's done here is already done here for you. And in the majority of cases, you will be able to use this. I recommend that you try to use this before doing that. Parameterization takes a lot longer. You have to do cross products and all that stuff. It makes it complicated. Which leads us to the divergence theorem, which says what? What's the equation?
So the flux of the absolute function, so vector field is going to equal to
right, the flux of this guy, right, this, remember, it's called the flux, is equal to the triple integral over some E
and
div f dv, right? And what's the conditions here? What's S and B?
S
E
surface,
is the
E is the
B is a solid
solid
region bounded by,
S, closed S.
right? So when we did that whole summary of calculus thing, we said that this was a common trend between all these theorems. It's always something bounding a region, right? So Green's theorem, everything was two-dimensional. It was a one-dimensional curve bounding a two-dimensional region in two space, right? R2, right? Stokes' theorem is about a one-dimensional curve bounding a two-dimensional region, but now it's generally in R3, right? So if you change things to R3, that's where Stokes' theorem comes in, right? Because Green's theorem can't handle R3. Green's theorem is just for R2, right? So Stokes' theorem handles R3, and divergence theorem is also R3, but now your solid is three-dimensional, and your boundary curve is two-dimensional. It's just a surface, right? And so that is actually divergence theorem. So that's the equation. Know when it applies, just in case you can use it. What was the other major theorem that we did today? Did in this class?
The fundamental theorem of line integrals.
Fundamental theorem of line integrals, pretty important. And what did that say?
If it's conservative, then you can do the endpoints.
In general, that's not what it says. That's a consequence of this theorem.
F of dr is equal to, no, that's Green's theorem.
This says if you are taking the integral over C of the gradient function, right, dot dr, that is equal to just the original function at the endpoint. Right? Writing down the layman's version here, minus the original function at the initial point. In other words, the curve C doesn't matter. You don't need to parameterize, you don't need to do anything. Just find this guy, which is called a potential function. And then you just evaluate it at the endpoints. All right? Right? And we know F is conservative if F is equal to gradient function for some scalar function. Right? So this implies, for example, that F dot dr equals 0 if C is closed. Right? So basically when you have a closed curve, the endpoint and the initial point are the same thing. And so this dies, right? But in general, it's not 0 if your C is not closed, right? You have to just compute the different endpoints. Right? So
Oh no.
what?
I've got a textbook on top of a vending machine.
You left your textbook on top of the vending machine.
Yeah, this morning.
Go get it.
Try to go get it.
No, but it was the.
It's recording.
Video.
Yes,
Come on.
video, yeah.
We'll pause for you.
But come on, that's like $150 or something, right?
We won't do anything to come back.
I'm flattered that he just threw away $200 just to spend time with me. But okay. So far, we're just going over concepts. I'm going to do some examples in a second, but
He's just
Right.
reviewing what's what.
right. So how did we find the potential function? First of all, how do we know something is conservative? Well, you don't have to always check, but you could check. Right? So let's say f is equal to a two-dimensional function, right? P, Q, right? How do you know f is conservative?
Derive P in respect to Y.
Partial.
Partial derivative.
F is conservative
When
Integral over
if what is it?
partial P
of respect to y.
respect to y
Yeah.
equals to q respect to x.
Right. And these guys are the continuous
Function.
on, you know, the open region, blah, 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 blah. There are a lot of things that we have to worry about. But in 392, they're always going to give you the nice situation, so you don't have to worry about it, right? But yeah, on any region where these functions are continuous on the curve C, and if this holds, then your function is conservative. What about if your f has 3 dimensions, right?
Oh, you integrate respect to
No.
right? No.
You have
Yeah.
to do the divergence.
F is conservative
Curl.
in this case if what happens?
Curl. Curl equals to 0.
Curl of f equals 0, right? So if someone asks you, for example, to do some f dot dr integral, right? And you know that if your function was 2 dimensions, this is true. And if your function is 3 dimensions, that is true. Then you can actually skip doing the line integral and just find the potential function and do it that way, right? Like I said, they're really going to test the concept, so they're going to sometimes be 2 ways to do a problem, and they're not going to ask you which way to do it. But you should know that, well, if one way is really difficult, I can switch to this way. Right?
So I was trying
Part 2, they're definitely going to say do it directly and the other way. But in part 1, I see more of these questions where it's like, you know,
Yeah.
Part one
But
flexible.
then you
do you really know the concepts that we're teaching in this semester, right? Because then your life is hard one way, but easy another.
In part one, you recommend like doing trick first, trying
Part 1,
to go for tricks first.
trick.
Trick.
No, I would go directly and use it, right? It's just if you see that when you're setting up directly, it's sort of complicated, I would consider doing it. If you're not specifically required to do it, then think of all the ways you can do something, right? But now, how did we actually find these guys? Right? Say we know f is conservative. How do we find f? Right? What was our process? It was just doing a bunch of integrals, right? We said
Isn't that exact value, exact problem, exact differential?
yeah, it's the same method used from exact differential equations, except we did a method where it was streamlined for us. But it was if you do this method in differential equations, it will still work out. Right? This is, let's say it was p, q, r, right? If this guy is a gradient, then it means that the p must be the partial with respect to x, the q must be the partial with respect to y, the r must be the partial with respect to z. Right? That's what it means to be conservative, right? Your f is actually the gradient function of something, right? This means that your f would actually be the integral of p with respect to x, and at the same time it has to be the integral of q with respect to y, and at the same time it has to be the integral of r with respect to z, right? So you can compute all these integrals and pick out the functions that show up, right? All right, so let's do an example, right? This is just an example, right? Let's say I did this guy, whatever it was, and I got, say, x e to the y plus sine z plus some constant. G of y z. And I did this one, I get x e to the y plus another constant. And here I got cosine z plus sine z plus another constant, j of x. Right? So this would mean your potential function is what?
The x e to the y.
X e to the y
X e to the y shows up,
Sine
plus
sine z shows up,
plus cosine z.
cosine z shows up, plus a constant, right? Right, just do all these integrals. Just integrate the first component with respect to x, integrate the second component with respect to y, integrate the third component with respect to z, and then pick out the distinct functions that show up, right? Right? This guy's a repeat, just ignore him, right? All your distinct functions that show up, the sum of those functions will be your potential function. And you just attach a k onto it, right? Right. right? And you can always double check, because when you have this one, if you take the partial with respect to x of this function, you should get the first component. With respect to y, you should get the second one. With respect to r, you should get the third one. Right? And if that doesn't happen, it means that your function really wasn't conservative in the first place. Right?
Okay.
So this method really streamlines the whole exact differential equation method thing that you learned in 391. But the problem is, it will always give you an answer. Right? The way you learned in 391, it actually doesn't work if it wasn't conservative. This will always give you an answer, so you should always check at the end. Right? So
this method will always work, right?
yeah, in theory, once you can actually integrate it and get an answer, you'll always get an answer. The question is, it might not work. Right? But when it is conservative, it will work. It always works.
Okay. Why is this method not taught in the book?
I don't know.
Plus some implementation, I guess.
Too easy.
Yeah, differential equation is already easy. Gotta make it easy. Okay. Is there any other concept I want to touch on in vector calculus?
Maybe arc length and all that stuff.
Arc length is, sorry, Calc 3. Sure, let's do an arc length.
Oh, that's going to be an exam, right? Our from Jhevon.
Yeah. So I guess now we can actually jump into practicing problems. I don't think I have to go through any concepts for linear algebra. That's all just like straightforward and computational. But yeah, let's practice some problems. Oh yeah, found it.
Look at this.
Okay, let's do an arc length one. This is actually a previous example that we did. Now we're getting to the problem section. Did an example like this, and I put a bunch of them on the first test, and one of the first quizzes that we've done. And here I told you that I only care from t equals 0 to t equals pi. So how do you find arc length? Yeah?
R prime of t, find the magnitude.
Yeah. Length is just the integral from between the bounds of the magnitude of r prime.
Yeah.
Right? So what we're going to do is find r prime, which here it's going to be minus 2 radical 2 sine 2 radical 2 cosine.
Is there guaranteed to be an arc length problem in our final?
I believe there was, yeah. I glanced at it very quickly because I didn't want to give away too much information and say something. So yeah, I think there was. So let's see. So the magnitude is just the sum of the squares of each component, and you take the radical, right? So you square this, you get what?
You got
Negative 8 sine squared t.
8 sine squared plus
Oh, it's 8.
8 cosine squared plus 1.
Oh, nice. Right. Square.
So it's going to be
Squared, yes.
9.
Right? Which now you can factor out the 8, you get sine squared plus cosine squared plus 1. That's just radical of 9. That guy is just 3. And so your length is just going to be integral from 0 to pi of 3 dt. Right? It's just 3 dt. But this is the main concept for arc length, right? Just when you're given a curve that's parameterized, you just find the magnitude of its derivative and you integrate over the limits that you're given. And that actually gives you the length of the curve. Right? So that's one problem. Let's do another problem. This is a surface area problem. I chose to do spring 2005 problem 5. So it says, you can see the question, I'm just going to write down the main points. The area of z equals 4 minus x squared minus y squared in first octant. Which means, they tell you this, but you really should have known that from the fact that they said the first octant. Yes.
Did you at least finish the extra key for the last exam?
I didn't rewrite it, no. I'll also post that between today and tomorrow.
Is this the surface area problem?
Yes, this is a surface area. Find the area of this surface which is bounded by this region. All right? What is this surface?
Parabola looking down.
Paraboloid, opening down.
Yeah,
right? So we have this guy come like this. Right? The maximum it hits is 4, and of course it hits the xy plane as a circle, right? If your z is 0, your circle's radius 4, right? So, and this guy is x squared plus y squared equals 4. But they said first octant, right? Where x, y, and z are 0, so it means they just want the part over here. That's the region D.
Wait, what problem is this? What are we doing?
Spring 05.
No, but
Surface area.
Surface area.
Oh,
Find the surface area. Okay. So find the surface area of this surface with this region. Right? And so
it's not really, it's not Cal 3 though?
it is Cal 3, yes.
Ah.
Okay, so how do we do it? How do you find surface area? The function is given explicitly, so you can just use the shortcut formula. You don't have to parameterize anything.
It's the integral of the whole vector, I think.
Magnitude of r times t times normal.
Area is the double integral of the magnitude of the normal vector, right?
Oh,
Over d. Okay? Now remember, we said our normal vector, we can get it in 2 ways, right?
there's
You can do the parameterization way, or you can do the shortcut way.
I'll do the
That's-
shortcut way.
radical.
We're given explicitly, right? Z is a function of x and y. So I can just say this is just minus fx minus fy, right? Doesn't matter which one I take, because I'm taking the magnitude. Right? So it won't matter. Right? So basically our area formula would look like the radical of fx squared plus fy squared. And that would give us partial with respect to x is just minus 2x, right? So you square that, you get 4x squared. Partial with respect to y is minus 2y, you get 4y squared, and plus 1, 8. Now how would you set up this integral?
Don't need to. We can just
That could
do,
just be
5.
4r squared plus
It'll
1.
be radical 9,
No.
so it should be 3.
Radical 9, how do you get radical 9?
Because I use polar.
Polar.
He
Okay,
substituted
in
cosine
polar,
squared.
what happens?
Because
It's gonna be-
x squared plus y squared is equal to r squared.
Right, so this would be the radical of 4r squared plus 1,
Yeah, sorry.
right? Times r dr d theta.
Yeah.
Yeah.
I think it's 9 cosine.
One thing I saw in the third test, I think. I don't remember if I mentioned it. Knowing that x squared plus y squared equals r squared is something that a lot of people apparently don't remember. They remember that x equals r cosine theta and y equals r sine theta. And they'd actually plug in 4r squared cosine squared theta plus 4r squared sine squared theta. And at that point you should be able to simplify to this, but they don't. And they continue this whole process of turning sine squared and cosine squared, and they use the half angle formula to integrate themselves. I'm like, what are you doing? X squared plus y squared equals r squared. X squared plus y squared equals r squared. Yeah, but so remember that.
Well,
It's good. You should remember that x is r cosine theta, y is r sine theta. But if you know it's x squared plus y squared, it's just r squared. Forget the cosine and sine. Just jump to r squared.
At least they did the half angle formula, right?
Well, no. And that's my point. It really gets messy if you keep these guys and try to do this. Of course they made a mistake. But they didn't have to, right, if they just realized that. Some people later on, like 5 steps later, they realize, oh yeah, I can just change this to r squared, and then they got it. But some people actually didn't make the jump, and they actually just tried to deal with cosine and sine the whole time. Which, you could do it, but it's just, you know.
Necessary.
So what's the limits on r and theta?
Well, theta is going to be from 0 to pi over 2.
Right. Remember that we're in the first octant, right? So it's only 0 to pi over 2. And r?
R is going to be from 0 to 4. No, 0 to 2. 0 to 2.
Right. This is r squared, so it's 0 to 2. Right? And you're just going to do that integral. Okay? How do we do that integral?
I would use u sub, make my inner one set the radical be u.
Yeah. U equals 4r squared plus 1, your du, or you can use u squared equals that, it doesn't matter.
Yeah.
Your du is equal to
8r.
8r r, and so 1 over 8 du is equal to r to r, and I can change the limits if I want. When r equals 2, this means your u would be equal to what?
1/4.
Plug in r equals 2, right? So that's 4 times 4, that's 16 plus 1, that's 17. When r equals 0, your u equals 1, right? So this integral I can write as integral from 0 to pi over 2, integral from 1 to 17 of 1 over 8 radical u du. This guy's just going to give me a pi over 2, right? Right? The outside integral with theta. Right? That's just going to give me a pi over 2. And then this guy I'm going to integrate. I think of it as u to the half, so this becomes u to the 3 over 2 times 2/3 times 1 over 8. So cancel that. It gives you pi over 24. 17 to 0 to 2 minus
Too much noise.
And since we have, like I said, we're going to mention the concepts more, so I thought I'd just revisit a homework problem for this one, for the next one. I believe this was section 13.5, problem 10. Talk about that. This was the problem where they were trying to trick you. This when we just learned about curl and divergence, which, by the way, let's actually talk about that. If I take the curl of f, let's say f equals for example, right? If I take the curl of f, how did we think of doing that? How did we do that?
I would use cross product.
Cross product, right? How do you find the cross product? Is you thought of it as del cross f, right? Where del was this convention where we just put the partials in it. Right? And so here would be partial with respect to x, partial with respect to y, partial with respect to z, and you put the functions here, and then you do the cross product, right? That gave you the curl, which means that curl is a function that maps from R3 to R3, right? So your input is a 3D vector, right? And your output was another 3D vector, right? That's what the curl, this is how it was defined, and based on the fact that we defined it from cross products as learned in Calc 3, means that the input is always a vector field, right? It has to be in 3 dimensions because we're taking a cross product, and the output of a cross product is another 3-dimensional vector. So this you should know. And we moved on to the divergence, where we say the divergence of a vector field f is equal to del dot product of this guy, which ends up being just the partial with respect to x of the first component plus the partial with respect to q of the second component plus the partial with respect to r of the third, or with respect to z. Right? So this guy, you know, this is a scalar. Right? So div you can think of as a function from R2 or R3. But then it ends up in R3, right? So input and
you mean
Rn in general,
R1.
right?
It goes from R2 to R3 to R1, scalar. Div?
To R1, yes. So this is, and it actually works in general for any Rn, but we only talk about 2 and 3 in this class. But so here it's important that the input is a vector, right? And your output is a scalar. In our class, it's just a real number, right? Right. So that's an important concept, and it doesn't really come up in the final, I don't think. But remember, the curl is the sort of guy that tells you how something was rotating around a point, and the divergence will tell you how something was diverging from a point. So, right. So those were the applications in physics and engineering, but that's how they were defined. And so you should be able to tell when you can do one of them and when is an expression meaningful, and of course you should be able to find them if they are meaningful. So in part 10, they ask you to say which one of these are meaningful.
Yeah.
Alright, so
Is that a full question?
they said curl f, there was another one with div f, there was another one with grad f.
So that's a full question? That's a full question?
Yes, it's a homework.
Oh, I thought it was a past final.
I haven't seen it on past final, but they are going to exploit this concept in your final. Curl f, right? Because they might ask you something, but you don't know if it actually makes sense, right? They'll put something like that. So I just want to make sure that you guys actually know when these things make sense.
So if it doesn't make sense, we just say it's impossible?
Yeah, something. Yeah, like I said, they're going to try to trick you with a lot of stuff. Right? They're not super hard concepts to learn, but you need to make sure you know them. This one is grad f. Curl of grad f div curl. Is actually the grad. Right? So which one makes sense here? Can I take the curl of f?
Yes.
No.
No.
No, f is a scalar field, right? In curl, your input is a vector, right? They put a curl in front of a scalar function. No, that does not make sense. Div f obviously makes sense. They even define that. So that's yes, because you have a vector function. What about the gradient of f?
Yeah.
Grad of f?
Yes.
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 Yes, that makes sense, right? That we learned in Calc 3. That's just, you create a vector with the components where the partials are the partial
You go
derivatives.
from
of the-
R1 to R3 or R2.
Yeah, R1 to R2 or R3 or anything,
Or Rn, yeah.
right?
Yes.
And
Yes.
divergence of grad f, does
Yeah,
that make
that makes
sense?
sense,
Right,
makes sense.
because if you take the grad of f, that gives you a vector function,
Uh-huh.
and yes, you can take the divergence of a vector function. So that makes sense. Curl of curl f,
Yes.
Yeah.
right. Because f is a vector function, so curl of f is defined, but curl of f is also a vector function, and it's still 3D, so you can again plug it into a curl. So yes, that makes sense.
No.
What about grad f times div f?
Not really.
Come
Yes.
No. Div is div of f is a scalar.
Right, this is a scalar, right? This one is a vector, but you can't cross product a vector and a scale.
Oh, that's cross, right?
Yes, this is a cross.
We haven't done that in like since like high school.
Huh? Yeah, really,
Like 10th grade in high school, so we
Yeah.
started doing that.
yeah, it's cross product. All right, so this does not make sense, right? Grad f, is that this?
You were on that.
Yeah, one of them was a typo. I think one was this guy. Does
No.
that make sense?
No.
No. Right? Grad, the input is a scalar, the output is a vector. Curl of the gradient of f.
Yes.
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 Grad f is a
Is the
Vector,
vector,
and then
yeah.
curl
and
vector.
curl vector is yes.
Yes, but it has a condition. If f is 3D vector. Right? Remember, curl is taking a cross product. You need 3D vector,
Okay.
right? If your f was a 2D vector, then it still wouldn't make sense.
Yeah.
Right? So on the condition, if your f is a three-dimensional, if your f is a three-variable function, which means grad f would be a 3D vector.
So you're saying that in the final they may tell us to do Stokes theorem for a two-dimensional vector field?
No.
Come again?
So are you saying that in the final they're going to ask us to do Stokes theorem in a two-dimensional?
No, because you can't
no.
do Stokes theorem.
Exactly. Trying to trick us.
And since battery's about to die, we'll take a break there and we'll